Okay, so in the previous video, we introduced the concept of an exact ordinary differential equation. It might seem a bit abstract, so I think it is best understood via an example. So here we have an ODE that we're asked to solve. Now, you're not always going to be told what class of ODE you are dealing with. So it might take some observation. Well, we notice that we have some nonlinear terms for the dependent variable, so it is a nonlinear differential equation. So that rules out using something like the integrating factor method that we saw in a previous video. Now, we looked at other methods such as separation of variables. Now, this is a bit messy and I don't really see how we might be able to separate these variables. Why don't we look at rearranging this and to see if maybe it might be an exact differential equation. So rearranging this, so we're going to multiply by the denominator. We're going to have something like sine of x plus x squared e to the power y minus 1 multiplied by dy by dx. And if we add the numerator to both sides, we're going to have y cosine of x plus 2x e to the power y plus this, and all of this is equal to 0. Now we might suspect that this is indeed an exact differential equation. The reason for this is that it is of the form m plus n multiplied by our y prime term here, and all of this is equal to 0. So this is in the same form of the total derivative, where again we have some quantity f which is conserved along a path. So we suspect that it might be exact, but we must test for exactness. So recall, the test for exactness is we take the partial of m with respect to y, which will be equal to the cosine of x plus 2x e to the power of y. And we take the partial of n with respect to x. So we see that the derivative of sine x with respect to x will be equal to the cosine of x plus 2x e to the power of y. So we see that both of these are equal. Therefore, we indeed have an exact differential equation. So if we have an exact differential equation, then the solution to the ODE, which is the function f, tells us that the partial of f with respect to x must be equal to m. So let's say that the partial of f, which we don't know yet, is equal to m, which is equal to y cosine of x plus 2x e to the power of y. So we're going to take a stab at it and see if we can come up with an intermediate form for our solution f. So we're going to integrate with respect to x. So if we do this, we find that f of xy is equal to y sine of x plus x squared e to the power of y. But now note that we integrated with respect to x, but there could plausibly be some term that involves the variable y. So here we have an intermediate form for our solution to the ODE, which we are calling f. So again, now note by definition that this term n must be equal to the partial of f with respect to y. So now we have a solution for f, but it is not complete because of this g of y. So what we're going to do, we're going to say that the partial of f with respect to y, by definition, must be equal to n. So let's take the partial of f with respect to y from this intermediate solution over here. So taking the partial of f with respect to y, we find that we have sine of x plus x squared e to the power of y plus the derivative of g with respect to y, and that must be equal to n. And n here is equal to sine of x plus x squared e to the power of y minus 1. So again, this is taken directly from n, from our differential equation. And this over here is taken from above, as we've taken the partial of f with respect to y. So comparing the left and the right-hand sides, we see that sine of x appears on both sides, and we have x squared e to the power of y, which appears on both sides as well. Therefore, dg by dy is equal to the negative 1, or integrating, we have, my apologies, we have g is equal to y. So we found our solution for g of y, which is just equal to y. And so now we can substitute it back in here. And we have our solution to the ODE. We have f of x, y is equal to y sine of x plus x squared e to the power of y plus g of y, which we found to be negative y. And in the most general terms, we could say that y sine of x plus x squared e to the power of y minus y is equal to, at most, some constant c. And this is our solution in an implicit form of our differential equation given at the start of the problem.